Yeah, thanks for having me. I'm really excited to give this lecture. I haven't lectured in a while, so you'll have to be patient with me. Right, so what I want to talk about in the next, say, 2.5 hours with breaks is deep generative models. Of course, even in 2.5 hours, I can't possibly cover all of them. So I've picked a subset that I think are very interesting. Yeah, and we'll discuss those. So can you hear me in the back? Good. So I'd like to keep it interactive. I think, you never really know how fast lectures go. So if you have a question, please just raise your hand. Instead of letting me ramble on if it becomes unclear, I'd rather you just ask me anything you want to ask. Okay, so what we're going to talk about today are 3 classes of deep generative models. So variational autoencoders, normalizing flows, and denoising diffusion probabilistic models. And after that, depending on how much time we have, we'll talk a little bit about my personal favorite application of deep generative models, and that's for lossless source compression. And we'll check a little bit, we'll try to find out what we need to do to deep generative models to actually make them lossless source compressors. So I'll try to have breaks at the minimum every 45 minutes. If somehow, I get a bit caught up and I don't realize it's already been 45 minutes, if you just tell me, then it's probably better for everyone, including me. So, okay, so we're going to talk about variational autoencoders first. I believe you've already had some lectures about variational inference. Of course, I don't know what's discussed, so we're going to do a small recap anyway. So I hope it won't be too boring. But yeah, it's kind of it's sort of like a necessary prerequisite to talk about variational autoencoders later. Okay, so approximate variational inference. You should have all heard about this by now. There's many different papers and reviews about this. My personal favorite one is Variational Inference, a review for statisticians by David Bly and his colleagues in 2018. And in that review paper, they state that the goal of variational inference is to approximate the conditional density of latent variables given observed variables. So let's try to unpack that statement a little bit. So what we typically in this scenario have is a data set of observed data, where here the observed data will be represented by the symbol x, and each data point is, say, xi. And right, for now, we're going to assume that we have a fixed model that generated this data, and we kind of know it. So later on, we'll try to go to the setting where we don't know the generative model either. But for now, we're going to do that. And we assume that this data was produced by this generative model with this decomposition, meaning that it's actually a latent variable model. So it's a distribution over a joint distribution over a latent variable z and the observed variable x. And of course, by marginalizing out this latent variable z, we could get back to the actual data distribution over x. And now the goal of approximate variational inference or variational inference is to get this distribution over z given x. So let's have a particular example for such a case. And the first one that we're going to look at is the example of a Bayesian mixture of k Gaussians. So we have k cluster means, which are represented by the symbol mu k, and they are distributed according to a Gaussian distribution. And for each, say, data point, we have a cluster assignment. And this cluster assignment will be represented by the latent variable z. So we have k clusters, so k cluster means, but for n data points, we will have n latent variables z. Okay, and these cluster assignments, because there are k different choices, are distributed according to a categorical distribution. And without any prior knowledge on the data point, we know that we're going to assume that assigning to randomly drawing a cluster assignment will be equally distributed among those k categories. And now we'll have if we have those two, if we have sampled all of the mu k's and all of the z's, we can actually sample n data points by sampling from the conditional distribution p of x conditioned on zi and mu. Okay, and this distribution will be a Gaussian distribution where it essentially picks out here the this inner product between the cluster assignment z and the vector mu picks out the cluster center or mean according to the kth say cluster index if zk is 1. Okay, so this is basically a generative model that creates a mixture of Gaussians with k clusters. And the joint distribution for this data set is fairly easy to write down, right? So we just multiply these distributions that we've seen before. But now the question in variational inference is that we want to infer this distribution over unobserved variables, so mu and z, given that we have observed a set of observed random variables x. You can see the, yeah. Okay, and now why is this so difficult? You probably all know this. It's because if we apply Bayes' rule, we get this term here, which is the marginal distribution over x, which is intractable. Because in order to get that, I'd have to integrate out in this equation all of the z's and the mu's. And for this particular case, at least analytically, you can't easily do that. So here, the inference problem is to infer that distribution. Okay. Now, as I said, in general, for all but the simplest cases, we don't know that distribution analytically. So we're going to try to approximate the inference with the variational distribution. And we do that by picking a family of distributions. So for instance, Q, which is this family of distributions, I could say only Gaussian distributions. And I'm going to find the best candidate distribution, small q, that lives inside this larger family of large Q. And I'm going to optimize it such that it minimizes the KL divergence between this candidate Q and the true posterior P of Z given X. Okay, and so here we have this Kullback library divergence, and I've written it out, where these expectations are with respect to Q. Okay, not great, but we kind of are going in circles because this KL, I can't compute it because I don't know P of Z of X, right? If I would know this, I wouldn't have to do this in the first place. Okay, so let's unpack this KL divergence a little bit more. Let's rewrite it. And in particular, we're going to rewrite this term, the P of Z given X, by using Bayes' rule again. And now we see that we can write this Kullback library divergence as the expectation over log of Q of Z, the log of the joint distribution, which we do know, plus log of P of X, which does not depend on Q, essentially, right? So if I now wanted to minimize this KL divergence with respect to Q, this is essentially a constant, right? So in the minimization procedure, I can kind of ignore it. So instead, we're going to, instead of optimizing the actual KL divergence, I'm going to sort of like flip the signs and maximize the minus KL divergence, where I basically left out this constant term. So now we're going to maximize this evidence lower bound with respect to Q, right? And so Q appears in both terms, because here it's used for sampling, and here it's used for sampling and for the log term. Okay, so now we have an alternative objective that will allow us to actually find, say, the within that family of distributions Q, the distribution small q that comes as close as possible to the distribution that we didn't know. Okay, so this alternative objective that we'd like to maximize is called the evidence lower bound. And why is it the evidence lower bound? Well, because it lower bounds the log evidence. Because if you do some rewriting, not terribly complicated, you can show that the log P of X, which is the log evidence, can be written as the sum of the KL divergence between this approximate posterior and the true posterior, plus this evidence lower bound. And we know that this KL divergence is always larger or equal to 0, which means that the elbow lower bounds the log evidence. Okay, so that's why it's called an evidence lower bound. Okay, so we're going to optimize this evidence lower bound with respect to Q, this distribution, and that ensures that Q of Z approximates the unknown P of Z given X, and that the evidence lower bound becomes a tighter bound to log P of X, right? So the better that Q of Z approximates the unknown posterior, the closer that this evidence lower bound is to the log of P of X. And we'll use that later when we're going to look at variational inference for autoencoders. Okay, now there's many different types of families that you can pick for this variational inference family. And I think the most simple thing you can do, and it's very often done, is the mean field variational family, where if this latent variable Z is, for instance, a vector, or it consists of multiple scalar values, you assume that this Q of Z is a product of distributions over each element of these sets, right? So if Z is a vector, we'll take this as we'll take the probability of the vector as a product of probabilities over the single elements in the vector. And these distributions over these scalar values can all be different. So this is called the mean field variational inference. And if we would do this for this example that we had before, this Bayesian mixture of Gaussians, we would, where our goal again is to infer this distribution, we would take as an assumption, or say a parametric form for our, say, approximate posterior, something that factorizes over all of the mu k's and all of the elements of Z. All right. And now, what happens if you pick a approximate posterior that's not flexible enough compared to the true posterior? So a mean field variational approximation, again, assumes no dependencies across sort of like the vector, the elements in Z, for instance, right? Now, what if the true distribution over Z, P here, is on the left side, it's this green correlated Gaussian distribution, right? So here, if I now look at Z1 and Z2, because this distribution is diagonal, there is definitely a correlation between Z1 and Z2. Now, our mean field variational approximation is factorizes in independent things, so there can't be any correlation. So it can only really be this nice circle, or it can align along one of the two axes, but it can't be diagonal. And so now, depending on which KL you use, you're going to see different behaviors as to how this mean field variation variational distribution approximates the true distribution. Now, what we see in variational inference is we are actually trying to minimize this KL, right? So it's the KL of Q of P. And in other inference schemes, you could actually optimize the reverse KL, where you take the KL of P, Q. Now, if you look a little bit into what this KL looks like, you will see that in the variational inference case, the approximate posterior doesn't like to have non-zero values where the true posterior is 0. So it likes to sit inside the true distribution. If you don't do that, you get all types of infinities. So that means that if you look at the variance in different direction, it's going to be overly optimistic, or it's going to be overly confident about its predictions, right? So where in truth, along this direction, the variance is quite high, because you've picked this factorized version of your approximate posterior, and because we have this objective, and because we have, no, all right, because we have this KL, it likes to sit inside it, and the variance along that direction is heavily underestimated, right? So this is quite a consequence of this choice. And if we would now do a different inference algorithm with the reverse KL, you will see that this distribution Q likes to cover all of the distribution P. So here, now in this case, it would overestimate the variance. And now similarly, you can see funny behavior if you're actually trying to match a ground truth distribution here drawn in blue with the two different versions of KL. So in the KL that we are using for variational inference, which is this case, as I said before, it likes to sit inside of P. And now depending on how you initialize Q, it will pick one of these two modes. So if I initialized Q to be somewhere to start with this mean somewhere here, it's most likely going to move and sit inside this mode. If I would have initialized it close to the other mode, after some optimization, it will end up in the other mode. Now, the KL divergence between P and Q would have the opposite behavior. It would sit basically to try to cover both modes. But in this case, I'm trying to approximate this bimodal distribution with a single mode approximate posterior. And now this thing happens that the most likely value sitting in the, according to the approximate posterior, it's actually sitting in a very low density region of the true distribution, right? So my highest value according to the approximate posterior is not at all a representative sample of the true posterior, right? So depending on how flexible your posterior is and which KL you pick, right, you can get into these funny situations. Now, of course, there's variational inference with many different types of divergences. So there's also something called the alpha divergence. I'm not going to give the actual equation. I also don't even remember it. But the point is that the KL divergences, both cases, say the PQ and the QP version, are special cases of this alpha divergence. And depending on how you set this parameter alpha, you'll see different behavior of the sort that we talked about before. So if you set this alpha parameter to minus infinity, you will see that it exactly, Q, will exactly fit one mode of P. And now if you set alpha 0, you get the KL divergence that we use for variational inference. If you set it to 1, you get something that covers both modes. And if you push it to infinity, you get something that really tries to cover everything. Okay, so now this was, I think, a brief summary of variational inference, and I hope I didn't bore you too much. Now we're going to try to use this in combination with autoencoders to create a generative autoencoder called a variational autoencoder. Okay, so as I said, variational autoencoders, they start from autoencoders. So let's briefly go through that again. So a deterministic autoencoder takes an input data point. In this case, we can consider this image. It pushes it through a neural network that has a bottleneck in the middle. And after that, it pushes it out through a second part of the neural network that has the same dimensionality as the input. And it tries to reconstruct what it outputs compared to the input. So it tries to match those two things. And that's why it basically only has a reconstruction term. And now this bottleneck that we've seen, that we talked about, is called code. And what's useful about these type of autoencoders is that you can actually use them to have this lower dimensional representation of the data as a sort of code or a compressed representation of it. And you can use that for all types of downstream tasks. Now, autoencoders can be made into generative models in several ways. So they can't only learn compressed representation of the data, but if you put a prior distribution on top of that code and basically lift it to an actual latent variable, which is distributed according to some distribution, you can actually generate new data with it. So what we do is basically after training, you sample from that, say, code distribution, the latent distribution, you sample a particular value or vector of values, and you push it through the second half of that network, and then we create new types of data points. So now I've turned my autoencoder into a variation of into a generative autoencoder by using the fact that I have a distribution over latent variables that I can sample from at test time. And now variational autoencoders are models that basically combine variational inference that we talked about before, amortize it, we'll talk about that a little bit, and also optimize a generative model that looks like the second half of this autoencoder. Okay, so let's talk a little bit first about the generative model. So a variational autoencoder assumes that we will have a joint distribution over the data, and this latent distribution, which is this code distribution, so to speak, right? So here we assume that it's factorized such that we will first sample Z, if you want to generate data from this. And if I now have sampled the Z, I can sample an X by sampling from this distribution. right? So this is why there's this graphical model that you see over here. So far, it's not an autoencoder at all. It's just a latent variable model where you can, if you would describe, for instance, this distribution Px of z with a neural network, you basically have half of an autoencoder. You only have the decoder part. And because it's a generative model, the desired objective is to maximize the log probability of x, right? So not the log probability of x comma z, but the log probability of the observed data. And if we now use this decomposition of P of x as basically P of x comma z and z marginalized out, we can write this objective in the following way. And you might think, okay, great, now I'm going to optimize this, but there is a bit of an issue with this. Does anybody know why this is hard to optimize? Also true. But so how would you normally, this sampling, how do we typically evaluate that in deep learning schemes? Right. Right. But now, where am I doing the Monte Carlo? But normally, if you want to approximate an expectation with a Monte Carlo sample, it shouldn't be inside a function that's nonlinear. Right, so now, if I want to basically say that this is the same as log of 1 over, say, if I draw k samples, P of theta xk, sorry, zk, this is actually not true.
Yeah, but we can do jet inequality.
Exactly. So what we kind of want to do is switch the order of the expectation in the logarithm so that the expectation is outside the logarithm, and then I can do Monte Carlo sampling. If I keep it in this order, if I do Monte Carlo sampling, this is not an unbiased estimator. Right? So I have to do something. And so that's where we can use Jensen inequality, as you just mentioned, and use an alternative objective. And so this surrogate objective is basically the elbow that we talked about before. Okay, so now we can show that this log P of x, this desired objective that we had before, is lower bounded by the evidence lower bound, where we sample now z instead of from the prior distribution, this P of z, I'm going to sample it from a distribution Q of z given x. Okay, so now I've introduced a new distribution, which is the encoding distribution. And now we need to basically optimize this objective with respect to the generative model parameters theta and with respect to this Q distribution. So Q of z given x is this encoding distribution, but so far there's still no autoencoder because I have said nothing about how I'm going to parameterize this encoding distribution Q. Okay, so as I said, what we've done now by introducing the surrogate objective, we have now an objective that we're going to maximize with respect to Q in this variational family that we talked about before, and the model parameters theta. Now in, say, traditional variational inference, you would optimize the parameters of Q of z given x for each x separately. So I could say, for instance, that Q of z given x is a normal distribution, where for each data point, I will separately optimize the mean and the variance of this distribution, which means that at test time, I have to do, for every single new data point, I have to re-optimize, right? Which is quite tedious. Amortized variational inference tells you, let's try to amortize or distribute this cost of estimating this inference distribution over multiple data points. Go ahead.
Yes, sorry, I didn't get it when you just said it. You said if you're optimizing for each mu and sigma separately, you need to do that for each data point. Why can't you do that for each batch of data points?
Okay, so good, very good question. So basically, what this variational inference version says, a non-amortized version, says that Q of z for instance, a data point xi, I'm now going to parameterize it as a normal distribution over z, even mu I and sigma squared I. Okay, so now each time I see a new xi, I have to re-estimate the corresponding mu and sigma. So no neural network, right? So it's like it's not like it's an output of a neural network. It's just some separate parameter that I have to optimize with respect to the objective. Now, in the amortized variational inference, I basically say that these mu's that we talked about before, I'm going to write them as a function of x. And that means that every time, if I've optimized that function properly, every time I get a new x, I can just input it into the function and get the corresponding mean and variance. And I don't have to re-optimize anything. So now I'm basically going to say that these model parameters of q of z given x, in this case, as above, this will be the mean and the variance. I'm going to parameterize them with a neural network, parameterized by, this is actually the wrong parameters, new parameters, phi. Okay. So now what I do during training is I'm going to optimize this evidence lower bound that we had before with respect to the generative parameters, just like before, nothing changed. And the phi parameters that now determine the parameters of this encoder neural network that determines the function that maps input to mean and variance in this particular case. Any frequently used approximate posterior, in this case, is basically the one I drew above, is where you take the approximate posterior for z given x to be a Gaussian distribution with a mean mu and a diagonal covariance matrix for a vector, which is just the same as saying that it's independent across dimensions, this mean field version that we had before. And a frequently used prior is one that doesn't depend on any parameters. It's just the standard normal distribution. Now there's many, I would say that's the vanilla version. There's many different advances that make different choices here that are more complicated and that sometimes has advantages. So variational autoencoders were introduced concurrently by in two papers by Dirk Kingma and Max Welling, and also by Danilo Resende, Shakir Mohammed, and Daan Bierstra. And what they do here is they do this amortized inference that we just talked about, and they do another trick, and that has to do with the fact that optimizing these parameters of this encoding approximate posterior is actually kind of tricky. So let's recap a little bit, because we've now actually introduced an actual autoencoder. We have this joint model for the generative model, right, that you see on the top left. We have the decoder model that takes a sample z and samples a new x. And we've said that we now have this surrogate objective that now depends on both the generative model parameters, these theta, and the phi's. And the phi's are the parameters for the approximate posterior. And now, because we have a neural network that maps from x to z, now I've actually created an autoencoder, right? Because now I have this q of z is the encoding distribution, which is the first half of this network. And I have this decoding network here. So now I have a variational autoencoder. That's great. Except for the fact that we have a few problems, but I'll get to that, I guess, not in this slide, but in the next one. And the first remark I kind of want to make is that a VAE objective is basically a 2-for-1 type of setting where I basically get two things, not for free, but I basically try to do two things, not only get a good generative model, but I also do inference, right? So I've repeated once again, the objective that we're trying to maximize and this relationship of the objective, the evidence lower bound with the log marginal. And now maximizing this evidence lower bound with respect to these two sets of parameters basically leads to the optimization of two quantities, because the log p of x in the bottom equation here does not depend on the encoder parameters. And on the right-hand side, I'm basically maximizing this term with respect to phi. Because the left-hand side is constant, if I'm maximizing the second term on the right-hand side, the left-hand side, the first term, this one, has to go down, right? Because the left-hand side is constant. So the right-hand side as a total also must stay constant. So basically, optimizing this objective ensures that this amortized approximate posterior tries to approximate the intractable posterior that corresponds to the generative model, right? So for any, except if you take a linear decoder, you can't actually compute in general this posterior. So that's why we have to do variational inference. But what's more, if this approximate posterior is pretty good, then the gap between this evidence lower bound and this log P of X is pretty small. So what we're effectively doing is we're actually trying to optimize the generative model to be a good log likelihood estimator, right? So we have two things here. We have a good log likelihood estimator if the inference model is good, and we're trying to create a good inference model. Okay, and now, unfortunately, there is still one hiccup to overcome, and that is the fact that the optimization of the generative model and the encoding distribution unfortunately are not both as easy as it seems. The generative model optimization is pretty easy. We'll go through that now, but you'll see in the slide after that the optimization of the encoding distribution is tricky, and we have to basically try to do something so that we can actually use our favorite backprop algorithms that are by now implemented in all of the modern deep learning libraries. Okay, so we do optimization of this evidence lower bound with standard backpropagation, where your favorite optimizer will at the very least need a gradient of the objective with respect to the model parameters, right? So we're going to try to do that. And of course, we kind of want unbiased gradients of the objective, right? So if I now write down my objective here, in this case, it's written, the elbow is written with this symbol, doesn't really matter. But then now I'm trying to look at what happens if I differentiate this elbow with respect to the generator parameters, which were theta. So basically here, I just wrote out this gradient with respect to the generator parameters of the evidence lower bound, which you can see over here. And now what's interesting to note is that this expectation value, right, you're not allowed to just swap them. You have to look at them. If this the distribution from which you sample in this expectation value depends on theta, you're not allowed to swap them. But in this case, there's no dependence on theta, because this is distribution over zx, which is parameterized by phi. So in this case, I am allowed to swap them. So I can just put the gradient operation inside the expectation, and then take the gradient of theta of these two terms with respect to theta. And now what I can do is I can, because this expectation is here, I can take a Monte Carlo estimate first. I can sample a z from Q phi. For instance, only take one sample, and then put that into log of P of theta and Q of phi, and then compute the gradient. Right, so now the sampling hasn't caused me any trouble. But for the encoder distribution, we will get into trouble, because now we're trying to take the gradient with respect to phi, and this expectation value depends on it. So I'm certainly not allowed to just swap them, because then I'm basically, what I'm doing is I'm basically missing out one term. If I apply the chain rule nicely, right, I would miss out on one of the terms, and I'm missing a part of the gradient. Okay, but ideally, I do want to swap them, because I'd like to do a Monte Carlo estimate first, and then take a gradient, right? Okay, now in this paper by Dirk Tingma and Max Welling and Danilo Rezende and his colleagues, they introduced something called the reparameterization trick, which tries to circumvent this issue of sampling and then trying to differentiate through it. So the idea here is that you try to separate the randomness of the sampling and the dependence of the sampling on the model parameters that you're trying to differentiate with. Okay, so I'm going to rewrite sampling z from Q of phi given from Q of z given x, such that it is a transformation of another random variable, which I'll call epsilon here, that does not depend on phi and x. But I still want it to be a sample from the distribution Q. Okay, and now not for all distributions, but for some distributions, you can basically show that you can define a function g that is a deterministic function of this random variable epsilon and phi and x. So if I now sample epsilon, after that I can just apply a deterministic function, and that will give me z. Now, how does this help? If I now have this setting where I want to take the gradient of phi of this expectation value, where the function that we're taking the expectation value with respect to depends on phi, and some function f that depends on z. Now, because this is a deterministic transformation, this g, we're assuming it exists for the moment, I'm allowed to write this expectation over q and f of z as an expectation over a distribution p of epsilon, and basically write z here as a function of epsilon. So this is the same thing. I'm allowed to do that. But now you see that now suddenly in this expectation operation, there's no dependence on phi anymore. So now I'm allowed to swap them, right? So now I've swapped them. And now I can take one Monte Carlo estimate or multiple, with multiple samples or however many you want, and then take the gradient of f of z with respect to phi, where the dependence on the sampling is now hidden in the fact that z is a function now of phi, deterministic function. And in this recent, which I think is very nice, introduction paper or review paper on variational autoencoders, also written by Berg and Max, they have this nice visualization, which I think really aids the understanding in why this will allow you to do backprop and why the previous version doesn't. So what you see on the left is the original form in which we would try to backpropagate. So the sort of like diamond-shaped nodes are deterministic nodes. So that means that if something comes in them, they're deterministic function of whatever inputs that node. Okay. And the round blue nodes are stochastic nodes. So whatever comes in that, whatever arrows come in them, you have to get that input and then stochastically sample that variable that appears in this round blue circle. So in the original form, before we did this reparameterization trick, we saw that z was a stochastic random variable as a function of phi and x, but there's a source of stochasticity. So if I now want to optimize my objective function, which I've now summarized as f, right, which depends on z, I would somehow have to go through the sampling step. But I can't really go through the sampling step. I don't know how to differentiate through that. And now what this reparameterized form basically does, it writes z as a deterministic function of phi, x, and epsilon, where epsilon is now stochastic. But because it doesn't depend on any parameters, if I'm interested in the gradient of f with respect to phi, I will never have to take that route through epsilon. Oh. Did I go? Did I go too far? Yeah. I will never have to take this route. So I never go, my backpropagation algorithm never goes through the sampling step. So this is why it's why it works. All right, so we've kind of talked about this sort of like a general form of f. Of course, in our case, the f has a particular form because we're trying to reparameterize the evidence lower bound, where we're trying to, this f is basically this term, okay? And now by using, again, the reparameterization trick, saying that z is a function, a deterministic function, g, which we're kind of keeping vague at the moment, of epsilon, phi, and x, I'm allowed to rewrite this expectation value like this, and basically say that z is a function here, and again, z is a function. Okay, so now I've applied the reparameterization trick to the variational autoencoder, assuming I can find this g, this deterministic transformation, which you can't always find. But as I said, the good thing is that now I'm allowed to pull this gradient through the expectation operation, and I can basically proceed as if nothing happened. Okay, so as I said, this doesn't work for all distributions, for all Qs, for all forms of Q, but for the, say, the vanilla version, say, which has a Gaussian distribution, you can write this down very easily. So if Q of z given x is a mean field version, meaning that it's factorized across each of its dimensions, where the distribution over each dimension is Gaussian, which is the same as saying that it's just a Gaussian distribution for a vector, where the covariance matrix is diagonal, then what I can do, the representation tricks, I can define the distribution over epsilon to be a Gaussian distribution, which is 0 mean and have standard deviation 1. And I can define my mu, my mean, and my standard deviation, sigma, I can parameterize them indirectly with an encoder neural network. And then if I write Z now as mu plus sigma element-wise multiplied by a sample epsilon, I have now effectively sampled from this Gaussian distribution, right? So for a Gaussian distribution, this is very easy. And even for a full covariant Gaussian distribution, where I'm including some dependencies for the elements of Z, I can do this trick. So here again, you take epsilon to be a sample from an uncorrelated standard Gaussian. And now I'm going to write Z as a sum of mu, which is a parameterized mean, plus some lower triangular matrix L, which has to have non-zero values on the diagonal, times matrix multiplied with this vector epsilon. And if you now write LL transpose, that makes up this covariance matrix for the Gaussian that you're sampling from. So this is a Cholesky decomposition. Let me check. Okay. Let me see. We do these results quickly, and then we can take a break. It's really warm here, no? Okay. So the first, say one of the two first papers that we talked about before showed that compared to earlier versions of an autoencoder, where the objectives for the encoding distribution and the decoding distribution were separate. So we have the evidence lower bound, right, which is the same objective for the encoding distribution and the decoding distribution, but an older version of the, or an earlier version of the autoencoder called the wake-sleep algorithm had a separate objective for the encoder and the decoder. And in this paper by Berg, he showed that if you plot this evidence lower bound for different sizes of the latent variable, so you can take Z to be a 10-dimensional random variable, 20-dimensional, anything you think of, you can see that the red lines here is the variational autoencoder, and the green lines here are these wake-sleep autoencoders. You can see that in general, it tends to do better for all sizes of the random variable, of the latent dimension, both on MNIST and on Freyfix. And what's more, what's kind of interesting is that the latent space for these variational autoencoders have an interesting, I'm sort of misusing the term, but topology. So it has an interesting characteristics if you sort of like start to walk over in this latent space. So what you can see on the left is we can take one particular data point, X. I'm going to encode it in Z with my encoder network. And now I'm going to take another data point, which I will, for instance, this one. So I've just talked about this one. I'm going to take, I've created, for instance, Z0. And now for this data point, I'm going to create Z1. And now I'm going to interpolate in latent space in between these two codes and decode them according to the decoder. And that will give me different phases, right? So the decoding part will always give you, as an output, a data point or something that looks like a data point. And you can see if you start to interpolate that, for instance, this interpolating between these two data points gets the face to rotate a little bit. And if you do it in this direction, you can see a smile appear, and sort of, I think it's even sticking out its tongue at some point. And you can see something similar, for instance, on the MNIST data set, where here it's interpolated between a 6 and I think it's a 2. And you can see that there's quite some order in the latent space. And in the paper by Danilo Resende, they observed similar things. So what you can see here on the left are generations of the model, which look, especially for that time, look pretty good. And here they've basically taken a variational autoencoder with only 2D latent variables, and they've plotted those 2D random variables with the color that corresponds to the identity of the digit that corresponds to the data point that caused that set, right? Now you can see that all of the digits with the same identity tend to sort of like cluster together, right? Even though in principle, there's not necessarily something really enforcing this structure in the latent space. So there's lots of work in variational autoencoders and autoencoders in general that talk about the representation of data points in the lower dimensional space. And you can see that there is actually something interesting going on. And now finally, before we stop for a little bit, there's one more contribution by the paper by Danilo Resende. we have this evidence lower bound, but for some cases, I kind of want to have an estimate that is closer to the actual log likelihood. So the evidence lower bound is a lower bound of the log likelihood, but I kind of want to get as close as possible sometimes. Sometimes I want to get the best estimate I can for the log likelihood of this model. And what they did in that paper by Danilo and also in the later paper is they defined, instead of this evidence lower bound that we've already talked about, they basically defined an importance weighted evidence lower bound where you draw multiple samples from your encoding distribution and you sum them inside the logarithm. And it turns out that if you increase k here, so the number of samples that you draw, this gets closer and closer to the log likelihood, right? And so basically, if you take k is 1 here and k is 1 here, these two things coincide. But so if you want to do an estimate, for instance, by comparing it to an autoregressive model, and you want to compare their log likelihoods, you typically take a lot of samples and you use this importance weighted version to estimate the log likelihood. And in later papers, this sort of like tighter bound was also used for training. And that sounds like a great idea, and in some cases it is, but it has actually, for the larger you make k, the signal for the encoder distribution actually disappears a little bit. So they are, it's not always clear that that's a really good idea, but okay. Let's maybe stop for a second and have like a 15 minutes break so we can all take a breather and continue after. I will promise to maybe take it a little bit slower. I will try to take more time for questions, but then you have to promise me to raise your hand if you have a question. Okay? Good deal. So we talked about variational autoencoders. Several people have already asked questions. Is there anyone else who thinks, I have not understood anything what you said? Please explain something again. Yes, tell me.
On the last slide, the log something. Why can we now sum over the inside the log? Why is that?
It's so this is not really, I wouldn't say this is like how to say that? It's not really a Monte Carlo estimate. Yeah. So here you're allowed to do that for other reasons, but you can prove that if you increase k, that this gets closer and closer to log p of x. So it's not only empirical, you can actually mathematically show that this is true. Any other questions? Yeah.
In this case, the final eventual estimate would be more than another sum, like another sum.
The on the bottom?
Yeah.
Well, which sum would you like?
Expectation of the expression in the last line. So we have estimated again.
Oh, yeah. So typically you take a Monte Carlo estimate. Is that what you mean? Yeah. Yeah.
Try and repeat the question because I can't hear the question.
Oh, yeah. Good. Should I repeat the previous two, or I don't even remember if I did. Okay, so the first question was, I think. Oh, it's the first question. I don't remember the first question. Oh yeah. Okay, so great, thank you. It was basically why somehow I'm now allowed to have a sum over terms in the logarithm, where before we said that actually, if that comes from a Monte Carlo estimate for an expectation value that's biased, this comes from another reason, not from that type of. It's not because you're taking a Monte Carlo estimate, and we talked about the fact that you can actually theoretically show that this is better. And the second question was, please someone else help me.
So two sums.
Two sums, yes. Whether or not there needs to be another Monte Carlo estimate to evaluate this in practice, and yes, you'll take a Monte Carlo estimate for this gradient. Thank you. Any other questions? No? Okay, so before we continue on to the next topic, I want to give a unfortunately very incomplete, but still some selection of advances in variational autoencoders, because of course the first two papers that we discussed, right, they were pretty seminal papers, but they're for deep learning, say criteria, pretty old. I don't think any other discipline calls papers that are 7 years old, but in deep learning, we say they age pretty quickly. And there's been lots of advances in variational autoencoders to try to make them better generative models. And one of the ones that I'd like to highlight is one that came fairly soon after the first two papers. And that is a so-called ladder variational autoencoders by Casper Sonderby and his colleagues in 2016, where they tried to improve hierarchical VAEs. Now, what are hierarchical variational autoencoders? What we've discussed so far are variational autoencoders where we have a data point X, a single layer of latent variables, right? So this is this part here that I just drew is the encoding distribution, right? Where we go from X to Z, and where the decoder goes from that same single layer back to X. And what you can do is you can add more layers of random variables, of latent random variables on top of each other. And then you can show that in principle, this can get more and more flexible, right? Now in practice, even though from a theory point of view, you would think, great, I'm going to have an even better density estimator. In practice, adding more and more layers tends to not help. It's a bit like making a neural network deeper and deeper. In theory, yes, it's great. In practice, it's not always that great, right? So what ladder VAEs did is they tried to take this hierarchical VAE with multiple levels of variational latent variables and do something to the inference model and the decoding distribution, such that now when you add more and more layers of latent variables, the performance actually does improve. And the way they do that is by basically changing the graphical model of the inference model. If I say graphical model, do some of you think, uh-oh, or it's all fine? No? No screaming? Okay, so basically what they do is, so what you see on the left, right, in this traditional hierarchical VAE, you can see that the dependency structure of X and the orders in which you sort of like these layers of latent variable appear is in exactly the opposite order in the inference model as it is in the decoder, right? So the inference model goes from X to Z1, Z2, where the decoder model goes from Z2 to Z1 to X. And now it turns out that if you sort of like take the inference model and make the order of the dependencies of Z1 and Z2 the same as in the decoding model, which then also allows you to share some parameters between the two neural networks, etc. Turns out that this actually works much better, and you get this type of ladder structure, and I guess that's why they call it ladder VAE. And what you can see on the right here is the our say evidence lower bounds. Let's look on the left here. So here we have the normal. We're plotting the normal evidence lower bound, no importance weighted sampling or anything, for the different versions of the VAE. So we have the hierarchical VAE, which is the red line. And we plot this as a function of the number of layers of latent variables, right? And as I said, theoretically speaking, you think more layers, better, so it should go up. But you can see actually that not only doesn't it even go up, it actually goes down. So somehow, in practice, just naively applying this doesn't really work very well. And now if you apply multiple tricks, including this sort of like weight sharing, this changing of the order of the dependency structure of the latent variables, and apply some weight normalization and blah, 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 you get this orange line, which does increase as a function of the number of layers, which is exactly what we expected. And so on the left plot, this is evaluated on a training set. In the middle plot, this is the evidence lower bound evaluated on a test set. Here you can see the same type of behavior. And on the right, you can see an importance weighted estimate, right? So here we take, for every data point, we take 5,000 samples of the latent variable. So this is super expensive to calculate. And here you see that for this tighter bound, tighter estimate of the log likelihood, we still observe this behavior that in this new model, which is the orange line, there is good improvement in performance, which you didn't see in the, say, vanilla hierarchical VAE. Any questions? So the question is this comparable to skip connections to normal autoencoders? I would say it is to a certain extent. But it's not exactly the same. So there are skip connections in this architecture, it's true, but the point really here is the difference in order. So on the left side, right, we see that in the inference model, Z2 is modeled as a conditional distribution on Z1. On the right side, in the inference model, which is here, you see that Z1 is conditional distribution on Z2 and not the other way around. Now, there are skip connections in there, and they do play a role because they make it easier to propagate the signal, but it's not the only thing. Any other questions? Yeah.
What are the deterministic nodes on the?
So so the Z layers, right? They're stochastic, so they're random variables. But the way that they try to enforce this dependence of Z1 on Z2 is by first doing a few deterministic transformations. So first I write D1, which is just some hidden layer in my neural network. I'm going to assign that label D1. I'm going to continue, create another one, D2. And now I'm going to parameterize the distributions of Z2 only with this, depending on D2. And Z1 depends on this deterministic value D1 and Z2. So they're deterministic hidden layers in the neural network. Yeah? All right. I have the feeling sometimes the microphone cuts. Is that true or not?
Yeah.
Okay. If I do this, you can sometimes not hear me, right? Okay. I should stop saying okay like this, but I have to look at my screen too. So okay. Now, one of the big criticisms of variational autoencoders are that if you don't do anything fancy, if you generate new data, these pictures tend to look a little bit blurry. And especially with the rise of GANs, that create pretty crisp pictures, it was long thought that variational autoencoders are great. They're very nice probabilistic models, and we all like manipulating these probabilistic models. It's very fun. But GANs produce better pictures. And now in 2020, of course, our field is pretty competitive, so people thought, I'm going to make VEs better again. And so there's this paper by NVIDIA with Nouveau VAE, where they basically scaled up something similar to a ladder VAE and applied lots of more tricks and applied it and made sure that now we produce crisp, high-resolution pictures. Right, so what you see on the bottom are really nice, at least compared to the training data set, pretty nice high-resolution pictures generated by this VE. So what is exciting, I think, about this paper is that although it has lots of engineering, which in our field is super important, this actually showed that if you put enough effort into it, you can get a VAE to produce really nice pictures as well. All right. So what I want to talk now briefly, not in too much detail, because I think you're going to have several hours of normalizing flows this afternoon. But I do want to talk briefly about normalizing flows anyway, because they connect nicely to variational autoencoders, and they can also be used as standalone generative models. Okay, so let's do a quick recap, summary slide variational autoencoders, and now let's see how normalizing flows fit inside variational autoencoders. So we had a variational autoencoder with this surrogate objective, which is this evidence lower bound, right? Which depended on the generator parameters, theta, and the inference or encoder network parameters, phi. And we knew that this evidence lower bound is equal to the log likelihood, the thing we actually kind of wanted to optimize, minus the difference in the KL divergence, I think there's a bracket missing, between the approximate posterior Q and the posterior of the generative model, which we certainly can't actually evaluate, right? So as summary, we know that by optimizing this evidence lower bound, because this term doesn't depend on phi, optimizing this essentially also optimizes this, and we're actually ensuring that the approximate posterior approximates the true posterior. That's why it's called an approximate posterior. And that because the sort of like this measure, not actually a measure, but sort of like this divergence that tells you how close this approximate posterior is to the true posterior becomes larger the worse the approximation is. This gap between these two objectives, say the surrogate objective and the true objective that you kind of want to optimize, becomes big if your approximation is really bad, right? And we've seen already before in the very beginning that if your Q is not very flexible, even in the normal variational inference sense, for instance, by taking a mean field variational approximation, which most models, most vanilla VEs do, you get this funny behavior that Q can't possibly actually match P, and we get into weird stuff. And so that means that even though, yes, the evidence lower bounds the log likelihood, there's quite a gap. Now, why is that a problem intuitively? Let's look at the log likelihood of this model and the evidence lower bound, which is a function of phi and theta. But for the moment, I fixed the encoder parameters, right? So I'm now fixing the encoder parameters. So I'm fixing this distribution, Q of phi. And now I'm going to try to maximize the elbow, the evidence lower bound, our objective with respect to theta. And now if this Q of phi is fixed, but it's kind of a really poor approximation to the true posterior, then optimizing this evidence lower bound will lead to this optimal value of theta. But because it's not very tight, right, because there's quite a gap, that's not actually very close to the optimal parameters of theta if you were to actually be able to optimize the log likelihood, right? So if our goal is to have a good generative model, we need to have a good approximate posterior that's flexible enough so that in principle you can shrink this gap as much as possible so that this shift, this possible shift between the maximum is as small as possible. So basically in summary, right, if you have a looser bound, the local maxima between the evidence lower bound and the log likelihood definitely don't really have to occur on the same position, right? Okay, and now that means that there is some motivation to try to make sure that these approximate posteriors can come from very flexible families of distribution, right? So far, we've only talked about Gaussians, which are unimodal. You can put some correlations if you want, right? But in the end, it's unimodal distribution, right? Whereas this true posterior, and where true means the posterior of the say the decoder distribution and the prior together, right? Especially for a complicated neural network, it would be very strange if that's a unimodal distribution, right? So we're trying to probably model a multimodal distribution with a unimodal distribution. We get into all sorts of weird stuff. Okay, so now we're going to try to apply a set of tricks to get this Q, this inference distribution, to be more flexible. And this was introduced based on a lot of prior work also by Danilo Rosende and Shakir Mohammed in 2015, where they introduced normalizing flows for variational inference. And the idea is as follows. I'm going to first take, if I want to sample from a complicated distribution over Z conditional X, I'm going to start with sampling from a simple distribution, right? And that random variable that I'm going to sample, I'm going to call Z0. And this comes from a simple distribution Q0, which is conditional on X. And in this case, what does simple mean? It means that I can sample from it easily and I can evaluate the log likelihood, right? So again, Gaussian distributions are always our friends. They simple, great. Okay, so now I'm going to sample one sample from this distribution. And now I'm going to apply a sequence of invertible functions to this. So I'm going to say I have these invertible functions. I'm going to denote them by fk, where k is the index of the invertible function. And I'm going to first apply f1, then f2, then fk. And what I get is therefore a sequence of random variables, right? I started with sampling z0. I apply f1. I get a new random variable z1, etc. So now I have a sequence of random variables. And because these, depending on how complicated these invertible transformations are, if you were to plot the density of these random variables, even though the first one is fairly similar, right? It's just a Gaussian distribution that's uncorrelated. Depending on how flexible, say, F1 is, I now already, after one transformation, may end up with a correlated distribution. So this is now skewed, right? Which is somewhat multimodal. If I keep doing this, I can actually end up with really funky distributions, right? And the funkiness here is sort of like determined by how you how the exact form of these invertible functions. Okay, I'll explain one more thing, and then maybe we can stop for questions again. So now, if we want to use this for relational inference, right, I always need to be able to actually evaluate the density or the distribution of my random variable, right? So even though I can plot all of the resulting random variables and get nice funny pictures, right? But I actually want to know what the exact density is at a certain point. And now what's cool is that these functions, because they're invertible, you can actually write down, for each step, you can write down how the density changes. So if I now, for instance, look at the transformation from zk minus 1 to zk, if I know the density of zk minus 1, which I here denote by qk minus 1 of zk minus 1, and if I can calculate this determinant of the Jacobian matrix, which is a matrix of derivatives of zk with respect to zk minus 1, if I can then take the determinant and then the absolute value and divide over it, then that's actually equal to the density of zk, that next point. Right, and now I can repeat that trick. And the good thing is that I said I started with z0, for which I knew the density. So I can repeatedly apply this equation and know what the distribution or the log likelihood of zk is, say my kth element in this sequence of random variables, because I know that the log likelihood of q0 of the corresponding z0, I know that I can calculate it and I can correct it with these terms. So that means that I've now, because these are invertible transformations, I've now actually created a way to sample for more complicated distributions. Questions? Yeah. Wait, lady in the back was first, I think, and then you go.
I just wanted to know, how do you make sure that F is invertible?
Good question. We'll get to that. That's really difficult. That's one of the challenges. Sorry, I repeat the question. How do I make sure that F is invertible? See my previous answer. Your question?
Yeah, I was wondering, I can see why you would need more complicated distributions for your Q of Z, but for variational uncoded, isn't it odd to have multimodal latent variables?
Can you describe? Okay, so the question is, isn't it odd to try to get a multimodal distribution for the encoded distribution of a? Maybe I can ask you a question. What do you mean by odd? So you find it odd. Can you explain why you find it odd?
Yeah, it's because it's like for a single X, it would have two codes in the latent space, right?
You always have a distribution over codes, right?
Yeah.
But it might very well be that that distribution is multimodal, right? It depends. There's not necessarily a reason why that has to be unimodal, right? The true distribution is given by if you take the decoding distribution and the encoding distribution divided by the normalizing constant, which if the decoding distribution is complicated, certainly by base rule, you'll probably get something multimodal, right? And so let's say that this latent variable has a meaning, right? If it's a compressed representation, there's no really reason why you can only have one very likely random variable, right? So the oddness depends on how you interpret. If you assign a meaning to Z, which if you really want to do that, you probably have to force it, right? Then it could become odd, but that assumes that you want to assign some funny meaning to it. Does that answer it a little bit? Any other question? Yes.
So these invertible functions, I guess they are also parameterized by something. They also have some parameter for. Then the parameters of these invertible functions, are they fixed? Okay, do we assign any distribution to these parameters, or we treat them as just points, sort of point masses?
Good question. So the question is, if you parameterize these invertible functions with, say, a neural network, for instance, right, with parameters, are those parameters again distributed, or are they point masses, yes, right? Yes. So the easiest setting is just to make them point masses, but then there's still the question on whether or not you want to make them functions of X or not. But we can get to that in a second. I'll try to explain it in a little bit. But the short answer is they're point masses, not distributions. Yeah.
The standard variation for the unimodal distribution, doesn't it also get multimodal by applying the decoder layers to it? Then also that unimodal distribution.
And so, sorry, the question is, in a standard variation autoencoder, there's a unimodal distribution, and if you apply the decoder to it, you get potentially a multimodal. And you're asking if that's similar to this. Yeah. So let me clarify. When you say the unimodal distribution, you're talking about the prior, I think.
Yeah.
Which is typically unimodal, right? Now, it's not really the same thing because the decoder there is not invertible, right? And what you're really sampling from, in your case, is you're sampling from, let me write it here, P of X comma Z, right? I'm sampling from a joint distribution because I'm first sampling from P of Z and then from P of X comma Z. Now, in this case, right, the difference is that because these are invertible functions, right, we can associate, for instance, it basically says that this term is a delta function because X is, if I know Z, there's only one particular value of X that you will point out, right? So it's a restricted version, I would say, of what happens in an autoencoder, in the decoder for an autoencoder. Right, so in a decoder, for instance, in a normal variation autoencoder, you sometimes probably say that this decoding distribution is a Gaussian distribution centered around some mean, which is a function of Z, right? So for one Z, I can have multiple possible X's. But if I would do something similar here, right? If I have Z and now I look at the conditional distribution of ZK on ZK minus 1, right? Which is a bit similar. This is actually a delta function, meaning that if I know ZK minus 1, there's only mass on the ZK that is determined by transforming ZK minus 1 with F. Right? So it's a similar but restricted version, I'd say. And what's more is that here, because they're invertible, this sequence of random variables ZK and ZK minus 1, etc., they're all of the same dimensionality. Whereas in the decoder, right, I go from a Z that's typically lower dimensional than X, right? And I can do that because I have no constraint on the fact that it needs to be invertible. So in this case, it's invertible, and it's hard to make something invertible if we go from lower dimensions to higher dimensions. Any other questions? I'm sure Diederik will have also many smart things to say about this later.
I kind of missed when, if you go to the previous slide, I think, the stuff with the fixed Q or the fixed phi. So basically, is the problem we're trying to solve with normalizing flows, minimizing the gap between log P and the KL divergence? I missed the.
Okay.
Yeah.
Okay. You missed the motivation for why we're trying to do this. Okay. Is that a good summary of your question?
Good.
Okay. So what we want to do, right, actually is optimize this objective, right? But I can't do that because it's not tractable. So instead, I'm going to optimize this objective, which is lower bound. And the difference between these two objectives is this KL divergence between Q and the true posterior. And now, if P, this true posterior, is very complicated, And if my Q can only be a Gaussian distribution, then I can never really actually get this to 0, right? So I want to find a new parameterization of Q that is not only Gaussian or not only super simple, that allows me to have a more flexible distribution so that I actually, hopefully, manage to drive this close to 0 as possible. And now I'm trying to find a different parameterization that maybe starts from a Gaussian distribution, but applies a sequence of transformations so that the resulting distribution is more complicated. And now what we're going to try to do is adjust these invertible functions such that the resulting distribution actually matches this thing. Okay? Yeah.
And in the end, since the transformations are in the latent space U, for the decoder, you sample from ZK, right? You're going to sample from ZK, not from the original Z0 convolution.
It depends on what you mean with sample, at what point you want to sample, because if I generate from a generative model, so the distribution that is matched with the prior in the evidence lower bound, right? In the evidence lower bound, let me go back for a second. This is interesting because this was actually a bug in one paper. So this is the evidence lower bound, right? Which has a KL divergence between the prior and Q, right? Now we will associate, we have many different Qs now, right? And now I will, I will associate QK, large K with this, right? So if I want to sample this from, if I want to sample from the encoder, I start by sampling from Q0, and then I go all the way to QK. But if I want to generate new data, because I'm matching the prior, P is matched with the last Q, I don't have to go through all those transformations anymore. I just sample from the prior and then I push it through the decoder.
So you sample from Q0, you don't sample from QK. Is that what you said?
So you sample from QK by starting from sampling from Q0, right? So I start to sample from Q0, apply these transformations, and then I've effectively sampled from QK.
Because like this don't have a nice way to sample from directly from QK.
Exactly. So I mean, sorry, the question is because we don't have a nice way to sample from QK directly. If we would, right, then we're sort of like back at the start of the problem because we didn't know how to sample from these complicated distributions. There was a question at the back at some point, yeah.
So like all these fancy ways that we have seen before, they were all based on
yeah.
And could use a mixture of what
yeah. So yeah. So the question is that all the sort of like the fancy VEs that we showed before don't have this, right? They have single Gaussians, and that was an observation. Remember you have the second part? Oh yeah, could we use a mixture of Gaussians? There are definitely VEs with a mixture of Gaussians, but a mixture of Gaussian has a discrete random variable in it, right? The cluster assignment, and the reparameterization trick for that, if I remember correctly, doesn't work. So you have to come up with funny other tricks to somehow differentiate through a discrete sampling procedure, which is actually really hard. Sorry? Closed? What? Okay, yeah, sorry, I don't tired of. We can talk later. Any other question?
Why do we need so strong transformations in the latent space? Like what can high level they learn powerful transformation? Can we give enough power to decoder in some sense that even if we sample from unimodal Gaussian noise, essentially it could still generate crispier images?
Yeah. So, sorry. The question is, if we make the decoder powerful enough, is this really a problem? Because it would probably know how to sample from even a unimodal distribution. Yeah, there's definitely people. That's definitely true in some cases, but in that case, your inference model still does, right? We have two goals, right? We have a good generative model, which would be satisfied by your proposal, but we don't have a good inference model, right? And if you want to do something with these latent representations for a downstream task, right? You still haven't learned a good inference model. So it depends a bit on what you want to do with your model. All right, let's continue. Where was I? Oh, okay. Did I already cover this? I think I did, huh? Okay, we finished this, right? Okay, good. Okay, now we've talked a little bit about the theoretical intuition behind this, but as always, there are practical requirements that are needed in order to make this normalizing flow actually be useful, right? So we're going to parameterize these invertible functions with neural networks. And ideally, right? So our goal is to get a very flexible distribution. But if I can only get a very flexible distribution by taking a huge sequence, then that's going to take me very long to sample from, right? Which means that during training, I have to go through this super long list of sequential operations, which is not very fun. So ideally, every component, every single invertible function that I apply has a lot of power so that it can already change the distribution a lot, right? Because if I can do that, then I probably need a shorter sequence, right? So it's important that these invertible transformations, although they have to be invertible, which is hard to satisfy, you also want them to be flexible. So there's some sort of trade-off there to be made. And on top of that, right, so we will have to, in our objective, there are terms that have to evaluate the log of Q, right, of QK, this last distribution. If you remember correctly, if I think it's on this slide, right, this log of QK is log of Q0 minus this sum, right? And it's the sum of the logarithm of determinant Jacobians. But determinants for general matrices, you know, they scale cubic with the dimensionality of that matrix, right? Unless you do something smart with the structure of that matrix, right? A diagonal matrix, the determinant is just a problem. So, or some, never remember. So, because we have to compute those determinants frequently during training and test time, ideally we do something to this structure of the Jacobian determinant, which you can do by basically choosing your f in a nice way, such that the Jacobian determinant computation doesn't scale cubic, but maybe linearly, for instance. And now I'll only go through one example, say the first normalizing flow for variation inference that was introduced. I'm sure Diederik is going to discuss many others with you later. But the first example of, say, normalizing flows for variational inference were introduced again by Danilos and Shakir Mohammed. They were definitely on a roll in 2015. And these invertible functions, they look as follows. So if I have a z, which is a random variable sampled from some distribution, so that's this one, and it occurs here, I'm now going to apply this transformation to it, and that will give me this new random variable z prime. Okay, now let's look at that transformation. So I've here represented in the bottom, oh, that's not good. Okay, I've here represented at the bottom, I've represented z as this vector. Okay, now I'm going to, the transformation first takes z and then adds something to it, and it adds something to it that has learnable parameters in it. So it adds this vector multiplied by this piece, which is a scalar. So this vector is learnable, this u has learnable parameters. So for each invertible, say, for each time you apply this transformation, you can adjust the u's, and if you adjust the u's, it becomes a different function, basically. And now what you see here, h here is an activation function, and it has to be invertible. So for instance, tan h, something like that. And inside that invertible function, we have, again, a vector of learnable parameters, w, and which is taken with the inner product with respect to this original z, plus a learnable bias. Okay. So this is pretty simple, but this is, so you basically sort of like, here you take the inner product, and then you sort of like shift the distribution by adding z to it. So now you can show that this is invertible under certain conditions. You have to put some constraints on U and W, but for most cases, this is invertible. So that's great. What is slightly less great is that if you look at this transformation, it's not super flexible. So one transformation of this can't do a whole lot. And the way to sort of like maybe realize that is if you would actually draw this transformation as a neural network, where you take Z as an input, and you get Z prime as an output. What this essentially does, it pushes Z through a single neuron, and then predicts something of the same size as Z again, so that's Z prime, and before adding Z back in. There's some bias term here. But you could, if you represent this as a neural network, this sort of squeezes it through a single node, right? Now, you've probably all optimized neural networks. This is not your favorite choice, probably, for a very flexible model. So this is also not very flexible. But it's invertible, although actually computing the inverse is difficult. So that's an important part here. You can prove that it's invertible, but computing the inverse in a closed form is actually quite difficult. And now we won't go through sort of like the details on this slide, but what's important is that the second practical requirement that we had, right, is not only that it's flexible, but also that the Jacobian determinant is simple to calculate. And this is where this method really shines, because the Jacobian determinant calculation, if you make use of this thing called the matrix determinant lemma, tells you that the calculation of this determinant, instead of scaling with d to the power 3, this is actually linear. So now I actually get a Jacobian determinant that's much easier to compute by using this trick. So not super flexible, but very easy to compute determinant. And so they showed in this paper many nice plots. And one of the things here is that you can do variational inference with these normalizing flows by trying to match this distribution that you see on the left or sequences of normalizing flows of different lengths. So in principle, you would expect that the longer you make that sequence, so the more transformations you apply, you have more variables to optimize, right? So you could probably get a more flexible distribution. And so you see that here, this is a sequence of 2 transformations. Here you have 8, and here is 32. And you can see that definitely the 32 is actually starting to do okay compared to the ground truth density. And especially compared to one of the other, say, normalizing flows that was introduced a little bit earlier, but not for variational inference. Okay, so before we move on to sort of like normalizing flows part B, any questions? Yeah.
I didn't get the point with the flexibility or like neuron in the squeezing with a single neuron. Where's this single neuron coming from?
Okay, so basically you're asking why does this formula correspond to the single neuron? Is that the question?
Yes.
Okay, so let's look at this thing. So here I've taken Z, and I'm only going to now focus on the red lines connecting these sort of like, I don't know what color it is. Not blue, but it's not green, turquoise. I'm going to see what causes this connection to a single node. Okay, and it's actually this point. So this, because I'm doing an inner product of Z with a vector and not with a matrix, right? I get a scalar out of it. And that's why you get that scalar node is this single thing. And then, and now then, so okay, this addition still gives you a scalar, right? And now I multiply it, that scalar with a vector. So that's how I get Z out again. And then
I was looking for U in the graph, but
so I would say U lives on these things, and W lives here. Yeah. Question.
Is there some more formal definition of the predictability property, like even some transformation, say what's the
So the question is there a formal definition of how you determine if something is very flexible, right?
Yeah.
So there are. So I think there's several papers that tell basically the flexibility of these transformations and the resulting distribution tell you something about how universal the resulting density is, right? Which means that how universal it is tells you how many different types of densities it can actually turn into, right? And I don't actually remember if planar flows are universal, but a generalization of planar flows called inverse autoregressive flows, if I remember correctly, are universal in the sense that they can under some assumption, if you take an perhaps infinite sequence of transformations, you can in principle get most regular distributions out. So there are theoretical measures for that, but the proofs are kind of finicky. I tend not to read them. Any other question? Okay. Let's continue. Okay, so now we've talked about how normalizing flows can be used as to make the approximate posterior in a variational autoencoder more flexible. Now, I only mentioned planar flows. There's a whole suite of other works. Maybe Dirk will tell you more about that later. I think he's also done quite some exciting work in this direction. What I'm going to tell you now is normalizing flows outside the context of variational inference. So no autoencoders, but really as standalone generative models. Okay, I have to keep an eye on time. Maybe let me quickly check how many slides this is. Either we stop here for a second or. Oh, okay, so we can do this this short section and then we take another break. I can stop messing this up. Okay, so generative normalizing flows, because again, no autoencoder. We're just going to try to use a normalizing flow, which is a sequence of random variables generated by invertible transformations, and we're going to use that alone as a generative model. Okay, so let's remember what we were doing, right? We had a random variable z0, which I'm now going to sample from a simple distribution that doesn't really depend on anything else. Let's say standard Gaussian. 0 mean, standard deviation 1. Okay. Now I'm going to apply an invertible transformation, f1, so that gives me z1. I'm going to keep doing that. So in this case, I've only drawn a sequence of 2. Now, how do I turn this into a generative model? Now, if I now take this sequence of random variables, I'm going to associate to the last random variable the random variable that actually represents observed data. So I'm now going to say basically that z2 is equal to x, where x is my random variable for the observed data. And in this case, I'm going to try to build a generative model for medical images, and that's why I drew this. I didn't draw it, I just copied this figure. Now, how do we optimize this? Because what we want to do, right, for a generative model, typically, is optimize the log likelihood. So how do we compute this? In practice, I'm going to take this x, an existing data point, as input. And now I'm going to apply the inverse of f2 to it. That will give me a z1. I'm going to apply the inverse of f1 to it, and that will give me a z0. And now I'm going to evaluate the density of z0 under the simple distribution and correct it with these Jacobian determinants that we talked about. Okay, so that together gives me the density of P of Z2, which is the density of P of X. So now, besides the fact that I've now, I can now optimize the log likelihood directly, no variation on lower bound, great. I have installed an additional requirement, though, a practical requirement. So right now, if I want to train, I have to go in the inverse direction of the transformation. If I want to sample from it at test time, I will first sample Z0 and go in the forward direction, right? Where I apply all of the normal transformations, not the inverses. Which means that I not only want F to be invertible theoretically, right? But I actually want to be able to compute the inverse easily. And what we have for planar flows is that although you can fairly easily show that it's invertible, actually computing the inverse in closed form is very hard. You can't actually do that. You have to have some iterative procedure. So that means that in this case, that would be very unpractical as a flow for this type of setting. Right, so for standalone generative normalizing flows, we have the additional requirement that the inverse needs to be easily computable. Any questions about that sort of like core concept? Yeah.
Yeah, you said in the planner, the last thing you said is planner flows wouldn't work necessarily. They don't give away the virtual function. Did I understand this correct?
Yes.
Okay, so now we're gonna see, like, we're gonna add the requirements that the method actually includes.
We're going to, yes. So let me repeat the question. Maybe I'll repeat the second part. We're now going to look at a different group of transformations that are not planar flows, that do satisfy the requirement that both the forward version and the inverse are easy to compute. So I'm going to change that. Okay. Yes, I can explain why planar flows doesn't do that. Let me quickly go here. Okay. So planar flows is defined at the top here. So I can write z prime, my new random variable, in closed form as a function of z, right? Now, if you want to invert it, I have to write the function that goes from f inverse from z prime. And I somehow have to now figure out what this f inverse is. And you can stare at this very long, but I mean, maybe some very smart mathematician knows it, but I certainly don't know what the inverse of this one is. And so there's numerical techniques to invert it. Some fixed point iterations, you have to do some optimization, but the closed form version of f is in this case not there. All right, any other? Yeah.
So just so I understand the setup, right? You still have your standard encoder and decoder structure for you to get to Z in the first place, Z0.
No, it's a very good question. The question is if we still have standard encoder decoder to get Z, and the answer is no. So Z is now no longer related to any encoding distribution. So you have to sort of like put the encoding part out of your brain and park it in the previous chapter that we talked about. There's no encoding distribution. Z is an unconditional random variable. So in the autoencoder setting, Z was distributed by conditional distribution on X, right? But here X plays a different role. Z and X are related differently. There's no encoding distribution. So Z here is just an unconditional random variable. It's a latent representation of X in a different way. So Z here, you get it by just sampling from a standard normal. So I take a zero mean, standard deviation 1 Gaussian, which doesn't depend on anything, and I just produce Z0. That's it.
I'm just trying to wrap my head around how you then get information. How does Z have information about the distribution of X? Okay,
good. So the question is, how does then, if sort of like Z0 is sampled from a distribution that doesn't depend on X, how does it contain any information on X at all, right? So it contains information on X if it was sampled by going in this direction. Okay, if I have a data point X, and if I push it, and that data point has been sampled, right, from some empirical distribution. If I push it through all of these inverses, then actually Z0 contains, actually the mutual information between Z0 and X here is 1. It contains all of the information that X has, but just in a slightly different form, right? Whereas, and they're of the same dimension, right? So I can fully recover X from Z0 because I just go in the other direction. But in an autoencoder, right? The whole reason why we have this reconstruction error typically is because Z is a lower dimensional representation of X, right? So it compresses information. So there's no compression here. Yeah, I don't know which one of you is first. Please pick.
Does it mean that, for example, if my X is some 4K image, then Z it's also some 4K noise?
Yes, so the question is if X is a 4K image or a very high resolution image, then Z is also. Yes, very true. It's also why they're quite expensive. Now there are tricks because they're invertible transformations, right? You can do memory saving operations by not always storing these intermediate things and recalculating them. But it's true that they're quite expensive. So they normalizing flows in this way have trouble scaling to high resolutions in a memory efficient manner. Question behind?
Yeah, it's kind of related to that. How useful is the latent code then?
The question is also very good. How useful is the latent code then, right? Because it's not compressed. We'll come to, I'm not entirely sure who will actually make that. I don't think we will. You can make it useful by, in this case, if Z0 is has a simple distribution, meaning that the random variables are uncorrelated, you can put that into downstream tasks which handle uncorrelated random variables better than dependencies. And one of these applications is compression. So you can use it for that. But beyond that, you can use them for interpolation and blah, 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 right? So they might have more. So for some applications, you want to do decorrelation of random variables, for instance, by trying to determine what, if you have an audio source with two people talking in them, so like distinguishing those two sources, you can somewhat map to this. But beyond that, the random variable x, z doesn't necessarily have to have a lot of use, except for the fact that in this way, we can optimize the log likelihood exactly, right? So we don't have a variational lower bound. So I don't have to do funny important sampling or whatever, right? Or I don't have to worry about some approximate inference scheme that has a gap with the log likelihood. That's one of the other advantages. Is it cutting again? Okay, strange. Okay, so I'll very briefly go over, I think, 3 classes of normalizing flows for density estimation. So as generative models standalone. And I think one of the most elegant and super simple ones was proposed in 2016 by Laurent Din. And that works as follows. I'm going to associate with my first random variable x, in this case, for instance, this image, right? I'm going to call that random variable x, and I'm going to split it in 2 halves. In whatever way you want, doesn't really matter at the moment. I'm going to split it in 2 parts. So let's imagine that x is a big vector. I'm going to take the first chunk, and I'm going to assign that x1. I'm going to take the second chunk and assign that x2. Now, I'm not going to do anything to x1. I'm going to define a new random variable that is also split into 2. And that first half will just be the same as the first half of x1. So z1 is x1. Great. And now the second half of z2, that new random variable, will be a transformation of the second half of x, where that transformation in this case is just a scaling and a translation of x2. And this scaling and translation is parameterized by a neural network that takes as input x1, the first untransformed version of part of x1 of x. Okay, and now, so basically what I'm doing is I'm saying I'm only transforming part of my random variable, not all of it. But if I do this in sequence and I switch the parts that I transform and which ones and the parts that I leave alone, in the end, I actually will transform all of the entire random variable. Now, why is this so nice? Because the inverse is super, super simple. So what is the inverse, right? So imagine now that I have Z1 and I want to recover X1 and X2, right? So you give me Z1 and Z2, and now you ask me what was the corresponding X1 and X2. So because we didn't do anything, right, to X1 we can just, again, copy it over from Z1. Good. And now X2, because I know Z1, and because I know that function that transformed thing, I can just basically put Z1 into that translation network and into that scale network and just divide and subtract instead of multiplying and adding. So this is the inverse, right? So this numerically is super easy to do, right? This is very numerically efficient. Doesn't take a whole lot of memory or speed. And so this method is called real NVP, standing for real non-volume preserving flows for real random variables. And the non-volume preserving relates to the fact that you have this scaling transformation, this scale part of the transformation, makes it such that this Jacobian determinant isn't 0, which is 1. Whatever. It's not a trivial, but actually you're sort of like squishing and stretching the distribution. If you set the scale to 1, you're not really changing any volume around the random variable. So that's why I call them a non-volume preserving normalizing flow. Now, even when this was published in 2016, you can see that definitely for that time, the image generations were pretty good, right? So this, although low resolution, on that resolution, the quality was pretty good. And since then, there have been many other generative normalizing flows. One of them is, for instance, masked autoregressive flows that doesn't do this splitting into 2 halves, but creates sort of like an autoregressive order between the sort of like the chunks of X. And if you go through a little bit more, then what you can see is that in one direction, which in this case would be the forward direction, this would be an autoregressive transformation, which is expensive. But in the other direction, going from data to Z, you can write that inverse of the transformation is actually not autoregressive. So that's easy to do. So at training time, you make sure that the direction from data to latent is the one that's not autoregressive, because then you can just, in one go, compute the whole thing. Whereas if you then want to sample from it, every time you compute F, I have to autoregressively compute it, starting from the first element of Z to the second element of Z, etc., for every single invertible transformation. It's pretty slow, but it performs empirically in terms of block likelihood. It performs better than real NVP. And then finally, of course, there was again a battle for saying, okay, normalizing flows can do high resolution images. They are really good. They're just as good as GANs, blah, blah, blah. And in 2018, Dirk Kingma and his colleague at OpenAI produced a paper called GLOW, which is generative flows with invertible 1-by-1 convolutions, which is basically a scaled up version of real NVP. So it has this benefit that it's fast in both directions. And it applies some 1-by-1 convolutions that it makes invertible and some other tricks, etc. And here you can see that actually the higher resolution pictures are actually pretty good, much better than we had before. Okay, so now what I wanted to talk about a little bit was denoising diffusion models, but I think we can all use Berg. So for those of you who were not in the room, your fellow colleagues have decided that I will talk about denoising diffusion models for the next 15 minutes, 10 minutes maybe even, and that the lossless compression, I can not possibly cover that in the last 15 minutes. So we're going to skip that for now. If you're interested in that, there's many exciting lectures by Peter Biel. They're all recorded, so please have a look at them. If you somehow want to hear me lecture, I can dig up some recording recently. Okay, so the last class of generative models that I want to talk about are denoising diffusion models. They are definitely the hype at the moment. And they're really nice models, and in some ways they actually look a little bit like normalizing flows, but not really the same. And they also look a little bit like variational autoencoders, but are not really the same. Okay, so let me go back. Denoising diffusion probabilistic models were first introduced in 2015 by Yasha Soldikstein and his colleagues. But they were recently popularized by a paper by Jonathan Ho and also in a slightly different version by Yang Sum. And so the idea is the follows. I'm going to take my data, and I'm again, as always, going to say that my data sample is actually corresponds to a sample from a random variable, right? And I'm going to call that random variable x0. And now I'm going to again apply a sequence of transformations that slowly corrupt this random variable into something with noise. And now, contrary to what we had before, these transformations that I'm going to apply are stochastic. non-invertible transformations. Right? So I'm basically, in this case, what you typically do is you take x0 and I add a tiny bit of Gaussian noise to it. And I keep repeating that over and over again. And if you do that many times, so for instance, what you could do is you could take x0 and you could define a Gaussian distribution around the original values with a tiny bit of noise. So that what you see in the bottom right, you can see more and more noisy pictures. If you keep doing this, in the end, for some types of sort of like noise distributions, you're going to end up in a stationary distribution where adding more noise doesn't change the distribution of the outcome random variables, right? So that's what it means to be stationary in this case. And so now we have this defined a process, a corruption process that adds noise or noises the data. Right, by a sequence, a very long sequence of tiny noising steps. And now the generative model comes from the inverse direction. And I'm saying inverse, and I really don't mean inverse in the sense of normalizing flows. I mean, it's just the other direction. Let me say reverse, probably better. The way that the generative model that we're going to train now comes about is I'm going to try to train a probabilistic model that matches the reverse denoising step on each thing. So for instance, where the kernel Q writes down the noisy distribution of xt given the previous slightly less noisy data xt minus 1, P of theta now tries to take xt, which is pretty noisy, and kind of recovers the slightly less noisy version of it. Right? And if you do that, I can generate new data by taking from the stationary distribution that I was talking about earlier, right? The super noise distribution that has nothing to do with data anymore, all the way at the right. Yep. I can, if I've trained my model properly, I can go in the reverse direction and sample something that looks like a data point. Okay, so that's the idea. And how are these models trained? They are trained again with a variational lower bound. We're not going to go through the derivation. That lower bounds the log of p of x0, right? And you do that by first writing down the joint distribution of x0 and x1 and x2 and all of the entire chain in the direction from x0 to xt. And then you write down the distribution that goes in the other direction. And then if you do that, you use Jensen inequality a few times again, you can write down something, even though the log of p of x0, you can't write it down because you have to marginalize too many random variables out. The lower bound is tractable, and just like with the VAE, you optimize that. Right, so it really looks like a VAE. Some people say it is VAE. And the objective here looks as follows. So it looks a bit nasty, but let's go over it step by step. So I first sample a x0 from my data distribution, right? Of course, I don't know the data distribution, so I basically just take a data point out of my data set. And now I sample a random time point, t, that is anything between 1 and capital T, right? And after I've done that, given this distribution, which is q of xt given x0, I sample from that distribution, which I could also do by basically sampling iteratively, right? First going from x0 to x1 to x2 to x3 to x4. But there are versions of, so if I say parametric forms of q, where I can, instead of having to do that sequentially, I can just do it in one step, right? And of course, our beloved Gaussian is one of those things. So what you do is I take the Gaussian of the distribution q of xt given x0, which I can hopefully calculate in closed form. And then I can compute the KL divergence between the posterior of the forward process. So Q here, the forward process is when you go from data to noise. The unlearned is the fixed thing. You basically calculate what the posterior is in the other direction. So you calculate that and you try to match the model, right, which goes in this direction to the posterior of the forward direction, right? So forward direction is this. The posterior of the forward direction goes in the reverse direction. At some point, you get confused about all the directions, but we're trying to match those. And so the way this is trained, in principle, you can do this for many different things. And what's really nice is that you can theoretically show that if you take a really long chain where every time your noise corruption is really small, right? So it's basically add a tiny bit of noise, that you can show then that if you choose a particular form for Q, let's say Q is Gaussian, all of your Qs are Gaussian, then you can show theoretically that the true reverse direction, the reverse direction that we're trying to learn, that's of the same functional form. So you don't know what the function, you don't know exactly, for instance, if Q is Gaussian, you can show that P is also Gaussian. You don't know which Gaussian, but at least you can guarantee that if you take a lot of steps, just tiny steps, that P will be Gaussian. So at least you're sort of like, when before we were worried by the inferential inference that our approximate posterior was Gaussian, even though maybe in reality it isn't. Here, if you take an infinitely long chain and small steps, you actually have to guarantee that it will be Gaussian. Right? So that's nice. Now we just need to make sure that if we take, if we make that choice to make it Gaussian, now we have to learn the mu's and the sigmas of that Gaussian distribution for every time step. So that's our goal. And so to train this in a practical way, right? In this objective, we've made a few assumptions, right? And the first is that I can easily sample from this distribution that makes a huge step, right? That goes from x0, so let's say that t is 100, small t, that I can immediately take x0, my data point, and in one shot, sample x100, right? But that means that I have to write down the distribution q of xt given x0 in a closed form, rather than having to apply this one-step version 100 times first. If I have to do that, then if I sample t as very large, it gets super inefficient, right? So ideally, I pick a q that has that property that I can, in closed form, make a larger jump. And a second, right here in this objective, there is this posterior of the forward process, right? So somehow I have to be able to calculate that in closed form. If not, at least the KL divergence computation becomes a bit finicky, which is not nice. So these are two practical requirements. And in, say, the most papers, these are satisfied because the following two choices of Q easily work in this case. So if you pick X, your random variable, to be a continuous random variable, and you pick all distribution Gaussians, then all of these requirements are easily satisfied. So that's great. What the other choice is, for instance, if you pick X to be a binary random variable. So if you have data, for instance, that's not images, but I don't know, some data that only has two particular values, then you can pick Q to be a binomial distribution, and you can also very easily do this. Right? So in this case, it's pretty, these choices, they work out. And so in 2015, when this sort of like method was first, I would say, introduced to the deep learning / machine learning community, Yasha showed quite some nice results, where on the top here, you see a data set on a Swiss roll, right? So top left, this is the ground truth data distribution, right? And if I now add some noise, if I'm halfway in this noising process, which is a large T over 2, I see a noisy version, right, of the data distribution, but I still recognize something. But at large T, at the end of this chain, there's almost no information about the original distribution, right? So I've destroyed all information about X in this case. Whereas in normalizing flows, right, if we take a step back, in normalizing flows, we're all invertible. So I could always reconstruct X given a set. But right now, I've lost all information out of it. And so here he showed that if you take this reverse direction and learn it, you can start by sampling from this distribution, the stationary distribution that you in principle know, and just apply this reverse distribution sequentially, and you can actually sample the same distribution. And so this was a nice proof of concept. And he also did something like that for CFR10 images, where here you can see some sample images. They're not amazing, but they look somewhat nice. Now in no, that's not the right one. So this is my last slide then. So in 2020, Jan Ho and his colleagues, they basically scaled up the work by Jascha Schultz-Dickstein. They scaled it up and they found a more efficient parameterization of this reverse direction. They did some really smart tricks and they slightly altered the loss function. And it turns out that doing that, and of course just having a much bigger neural network on it with all the things you can think of that usually trains well, they actually showed that these diffusion models produce images that are really of state-of-the-art quality, right? So before, log likelihoods, for instance, were always dominated by autoregressive models that we haven't discussed, but they're dominated. What you can see here, for instance, is that this row are metrics for an autoregressive model. And although the negative log likelihood, where lower is better, is still a tiny bit lower than the ones from the best model in the Gaussian diffusion model. If you look at other metrics that tell you something about how realistic or how much the images look like compared to images from the training data set, is a quite a complicated metric. There, for instance, this FID score, lower is much better. The difference here is huge. So the images generated by a diffusion model compared to, for instance, an autoregressive model, at least the one that they show here, right, are much crisper than and much more have much more of the same statistics as images in the training set than the ones generated by an autoregressive model. So this paper caused like a whole new rage of everyone who wanted to do work on diffusion models, and it's really cool. And there's active work on this. You can do this more on. I won't go over. You can do this for other types of discrete random variables. You can pick a different distribution for your Gaussians, but a different one, and you can do all types of tricks with the loss and you name it. They probably tried it. It's really exciting direction. So yeah, if you're into that, definitely lots of papers to read, I think. And I think I'd stop there. And I think we have 3 minutes time for questions, and maybe we can do the rest then on the way to lunch or something. Yeah.
Perhaps we have a stupid question, but like, how do you ensure the stationarity of the very last factor of your chain? So yeah. But do you actually enforce it, like you just clamp sort of the mean or variance, or you kind of ensure this by applying this finite transformation of the Gaussian? So
it's actually a really good question. So the question is, how do you ensure that there's a stationary distribution, basically, right? Yeah. And so for some choices of Q, you can calculate what the stationary distribution is. It's known. You can basically integrate out all of this, and you can show that the stationary distribution exists. And for instance, if you were to have a discrete random variable, you can put some restrictions on your Q that will, with some theorem, or it's not even theorem, you can easily prove if you put that restriction, you always go to the same stationary distribution. So,
for example, it can be like a regressive sequence, like if you.
Yeah. So an autoregressive sequence, basically, if one step Q of xt given xt minus 1, you can make that autoregressive and Gaussian, then probably it works. But you have to think a little bit. It's not, I think, for as soon as you go away from Gaussian stuff and you keep being in continuous space, you probably have to think a little bit about it. But there's a whole literature on Markov chains that talks about this. So, probably best to look into that. Okay, I think if it's a short question, we can do it. Okay. Do you have a short question?
Yeah.
Okay.
How do you think in this case, it retains the neighboring pixel information that we know in step? Like the spatial information that generate, like in normalized or some autoregressive model, you have to put from the previous frame.
Yeah.
To see that the next frame, if I'm generating that this pixel is a hair, so next will be a hair tree. Well, in these model, do they have some sort of mechanism where they get information from the pixel?
Yeah. So the question is, how do you make sure that in your noising process, you keep some non-local information in there, right? So if you, for instance, if you make your noising distribution Gaussian, you can, or in the reverse process, right? You have to predict a mean and a variance, right? So those mean and variance, that will be factorized, but it can be a function of the elements of X, right? So just like in the variation autoencoder, in the decoder, typically you pick a factorized distribution, but the parameterization has the parameters, say the mean and the variance, they depend on all of the other ones. So it's a bit similar to that. I think we have to stop, because I'm sure we're all hungry and we want to get in time for food. So thank you all for your patience, and yeah, enjoy lunch.